Hi, my name is Ben Sigelman. I'm a co-founder and the CEO here at Lightstep, and I'm here to talk about resources and transactions, a fundamental duality in observability. I've spent most of my career working on observability. I was at Google for 9 years in the beginning of my career and worked on Google's distributed tracing system called Dapper and their high availability monitoring and metric system called Monarch. And then Lightstep, of course, has been focused on observability as well. And it's taken me a long time to get here, but I've come up with a different way of thinking about observability than I used to. And this is what the talk is about. So without further ado, let's get started by talking about transactions. All right, so what are transactions? Here's on the right, you see kind of a diagram of some kind of system. We're going to be talking a bit about things from the perspective of this bank account service, which is in the midst of some larger microservices architecture, some cloud native architecture. And a transaction in this presentation anyway, it's not necessarily like a dollar, a banking transaction. It just means any kind of request that propagates from one part of the system to another, or not, but just an entire request. It's all the work that it does until it gets back and completes whatever it was trying to accomplish. So a transaction are the things in your application that actually, quote unquote, do something for their end user, whether the end user is a human being, or in some cases, if it's Twilio or something like that, maybe Twilio's end user is actually just another program somewhere running a script. But transactions are what deliver value to users or customers. These days, especially for cloud native, transactions are distributed. They don't literally have to be, but they often are. And they can be described at many different granularities. So but by that, I mean, the same transaction could be described at a very coarse granularity, like just an entire end user workflow. Like if you're a ride sharing app like Lyft or Uber or something like that, the entire flow of requesting a ride might be considered a transaction, and that's the only level of granularity you have. You might want to get a little bit more granular and think about the individual requests between services, like the HTTP requests. So you might think of that as the granularity you want to use to describe things. Or maybe you want to get more detailed further and look at some or even all local function calls. And then I suppose theoretically, you could look at a transaction in terms of every single CPU instruction that happens across the entire system to accomplish a transaction. And those are all valid ways of modeling transactions. Of course, as we get down the list, the cost of recording things at that level of granularity gets higher and higher. And in fact, it can get so high that there's a lot of overhead and you start affecting the transactions. But theoretically, these are different granularities. Okay, great. Now, the telemetry we use to describe transactions are usually traces and structured logs. And structured logs being, like a textual logging statement, but with clear key value attributes. Those things are illustrated here. You can see that the bank account request has a request size attribute, some kind of HTTP path, status code, latency, that sort of stuff. So these are theoretical attributes in this model for the pieces of the transaction. And I would argue as well that tracing will eventually replace logging. It will take time, but for transactions specifically, tracing will replace logging. I'll try to motivate that right now by showing you how much more flexible the tracing model can be than simple single process logging. By the way, I'm not talking about 2021 here, but this is more like zooming out where observability is going. So here's a logging statement. So you have some pseudocode here on line 22. Each one of these logging statements really defines its own table. You have a series of keys that are defined by the struct here, request size, path, status, latency, reflected over here. These become the columns of this table, and then the values, which are pulled from local state or whatever, those become the set of values become the rows in the table. So to spell that out and make it clearer, you have this logging statement as the code runs in production is populating this theoretical table. I'm not suggesting, of course, that we actually take this data and insert it all into MySQL or something like that, or even necessarily that we insert it all into Elastic or Splunk or something like that, but just that there's a theoretical table that's being described by the logging statement itself. and that you can model things that way. And in some cases, you have tools that allow you to run queries against those tables. What's cool about tracing is that these logging systems typically make it's quite difficult or impossible or expensive or impossible to execute flexible joins. What a trace is doing, a distributed trace, is doing a join across the entire system. So again, if this is your system architecture, what we're going to do is implement a join of all of the structured events, whether you call them logs or trace spans, it doesn't really matter, but you're still describing the transaction, and we're going to use the tracing context to join the structured events from all these services together into one much larger table, where you have a table that has columns from these different services, color-coded here, where service A, B, and D are also joined across. And then each distributed transaction represents one row in this table. And this is really powerful because if you can think of things in this conceptual model, it's possible to run all sorts of analyses to figure out, correlations between columns across service boundaries, which in turn allows you to understand how behavior in one service might be affecting some sort of behavior in another service. So, to be concrete about this, it's possible that you'd have a customer ID field in service A at the top of the stack, and you might find that certain customers are involved a higher percentage of the time when, let's say latency is high in the bank account service. And then that gives you something to go on, like how did that customer change their workload or what have you. So these sorts of joins are actually a really important mechanism to understand cause and effect across service boundaries. And if you've been wondering what all the fuss about distributed tracing is, if you think of it in this model, distributed tracing is really a join for your structured logging statements, and then a bunch of semantics and query capabilities on top of that. Okay, so that was transactions. Next, we're going to talk about resources. So what's a resource? So resources are the things that transactions consume in order to do their work. One side effect of this definition is that by definition, a resource is finite. So a resource can be something like your Amazon bill is a type of resource. Again, many different granularities. The amount of throughput through a Kafka topic, a Kafka cluster can only support so much load. And when you get to the end of that load and you've consumed all of it, things get really bad really quickly. You end up with a lot of pushback and very high latency, dropped requests, things like that. Similarly, CPU usage is totally fine until it's not. But as you all know, if you saturate CPU in a service, all sorts of things break that you took for granted. Even worse for memory usage, where the process just straight up crashes. But you can also get really granular and talk about individual mutex locks, for instance. If you have a lot of contention on a single lock, you'll end up with a read lock, which should be 150 nanoseconds, can take a million times as long if there's a lot of contention for a lock, and that causes problems too. So these are all types of resources, and what makes a resource is that they survive across transactions and that they're shared across transactions. And it's critical that you do share resources, because if you don't, your system will be incredibly expensive. Like, that's the whole beauty about running in a multi-tenant, multi-request environment, is that you can make better use of the resources and share them across transactions. Okay, so that's what resources are. To make this a little bit more visual, I've drawn these boxes for microservice, a Kafka cluster, and a mutex lock. These just totally illustrative. I'm sure there's better ways to measure the health of these things, but for a resource, the health is really what you want to show is what you want to think of. It's the amount that remains of that resource, right? At some level, or it's an indicator of how much that resource has been consumed. So you can see that CPU usage can spike, RAM usage can spike. You can see that consumer lag or producer lag is an indicator of health for a Kafka cluster, or the duration that you have to wait to acquire a mutex lock is an indicator of health for a mutex. So any resource has some kind of health metric. What I'd want to emphasize here is that none of these is meant to be an indicator of it's not an indicator of the success or failure of an individual transaction. It's although certainly when things like CPU and memory usage spike, you have issues with transactions. It's meant to indicate the health of the resource. And I'll talk about why that's relevant in a minute. And then the resources also have a bunch of tags. And this is actually really important. And I'll talk about this later as well. But if you're with me so far, the purpose of these tags or attributes, in my mind, is manifold. Of course, if you're just trying to understand and disaggregate, so if you see a spike like this, you might want to group by region or group by cluster ID or something like that, and that's fine. And you should be able to do that in a time series database. But more importantly, these tags are the lingua franca to communicate about resources and transactions. When a transaction crosses a resource, ideally, the transaction in some way is annotated with that resource, and it can serve as a way to join from the transaction data to the resource data or vice versa. And that's a really powerful thing. And I'll talk about that later when we get into an actual example. So I had said that there are different granularities. There are also a hierarchy. This is true for transactions, but I think that it's more important to make the point here. You might have a Kafka cluster, which itself has many microservices, and within those, you have a bunch of VMs, and within those, you have a bunch of mutex locks. So these things kind of level up and level down too. So there's hierarchy in the resource landscape as well as just these health metrics. Okay, cool. So on to part 3. So we've talked about transactions. They're the things that actually do work that your customers care about. We've talked about resources, and they're the things that make transactions do something and are shared across transactions. These are codependent. So let's talk about what that means. So here's a diagram of these resources, and these green squiggly lines are meant to illustrate transactions flowing into or out of those resources and doing their work. And you can see that the transactions are going, in this case, to different HTTP endpoints, in this case to different Kafka topics. In this case, you have readers and writers trying to perform their lock on the mutex. There are different types of transactions, and we would like, when a transaction crosses a resource, for it to be annotated with the identifiers from that resource. So if this topic Y request is coming in, that transaction, in terms of that schema of different levels of granularity, it's quite valuable if you ever want to be able to understand how the resource and the transaction interact. For the transaction to be annotated with the region and the cluster ID for a Kafka instance that it's using, or for this endpoint for the transactions to be annotated in the trace with something like the host name or container ID, the service name, the version, that sort of stuff. So again, you can use the tags from the resource to annotate the transactions and serve as a map between these two worlds. Yeah, so this is an illustration of that. The green things are basically traces, and then in the resources, you typically use metrics, telemetry, time series statistics to represent the health of these resources. Not always, but typically. Okay, so resources and transactions are completely, totally codependent, and that's a really, really important problem, which is to say, if your resources are unhealthy, the transactions suffer greatly, and if the transactions become too numerous, the resources suffer greatly. One of the things that bugs me the most about continuous integration as a topic, actually, I mean, I think it's great. I mean, of course, we use CI at Lightstep, but there's this idea that code can even be correct or incorrect without knowing what the workload is. And I think that's a total mirage. The only way you can know if, at least for system software or backend software, if the code is correct or incorrect, is to run it under a real workload, because the workload is actually really part of the semantics, and all the tuning around how resources are configured and even how resources are designed and implemented. It depends in large part on what the actual workload of transactions looks like. So it's not just that you might need more of something, but you might actually want a different thing. I don't like when people hate on MySQL too much. I mean, I hated on it a little bit earlier about certain types of data, but it's perfect if your data can fit easily on one machine and you just want relational semantics. there's really not that much wrong with it, aside from some of the replication issues. And similarly, if if you want something that's truly planet scale and cheap, like you're going to have to move off of that model into something else. So resources really can't be considered correct or incorrect from a design standpoint or from a code standpoint until you consider the transactional workload as well. And observability turns out to be one of the easiest ways to understand how the workload is affecting the health of the resources and vice versa. All right, so speaking of codependency, the end users, the customers of your application, they only care about transactions. And by that, I mean, if you have an outage and someone's trying to write up a report for, especially for a non-technical end user, they really don't care at all about the fact that you ran out of resources. That is like not their problem. It's your problem, not their problem. They only care about whether the transactions were correct and came back in reasonable time. So correctness and latency, and I mean correctness also implying that it wasn't an error. Correctness and latency are the two things that a customer or end user will care about for their transaction, and kind of nothing else. And how you accomplish that is up to you. The trouble is that for an operator, whether, by operator, that includes, DevOps, SREs, et cetera. For an operator, the only thing you can control are your resources. The whole point of software is that we're not sitting there taking the facts from the customer and then filling out some stuff and then doing some work as a human being. We're writing software to automate that stuff, and that software runs on resources. So operators totally sensibly are mainly concerned with resources because that is actually the point of control that they have. And end users only care about transactions. And the end users and the operators are codependent in this way as well. If end users change their behavior too quickly, it can create resource issues for operators. And obviously, if operators end up doing something that damages the health of a resource, then end users suffer. So end users, operators, transactions, resources, they're all codependent in this way. And there's this relationship between them. Right, I just said that. So end users and developers, or developer operators, are also totally codependent. And I think that's a really interesting, and to me anyway, kind of a profound thing, that end users and transactions, operators and resources, that's what they tend to think about because that's what they can control and what they deal with, but they're actually totally different planes that intersect in the workload itself. Okay, so, what do we actually do? This sounds like a problem. So it's necessary to be able to pivot between these two across telemetry types, metrics and traces, in the aggregate via tags and automatically. And this is the way that you can take some kind of scarcity on a resource or a health issue with a resource and pivot to understand how the transactions have changed, or you can go from a transaction being really slow or returning an error and figuring out which resource has something to do with that, because it's almost always going to, like, high latency is almost always going to be some resource that's under contention, whether it's your database or a Kafka queue or whatever. And then trying to understand why that's under contention is going to be a matter of figuring out how some workload has changed. Like someone pushed new code that increases the number of database calls by 100x, and that's why your database got slow. So it's an interesting thing. You're often pivoting between transactions being slow, finding a resource that's under contention, and then realizing that someone increased their load by 100x. So again, pivoting from transactions to resources and back again, or vice versa, right? And this is really hard because metrics and traces right now, people integrate them in the front end, but they actually need to be integrated at the data layer to make this possible. And it's a very difficult data engineering problem because the data actually looks quite different. Metrics are typically represented as time series statistics, traces typically as structured events and some whether it's spans or logs or whatever. It's basically a bunch of structured event data, not statistical data. So it's hard to pivot between them. And again, the tags are the way that we do that. And then finally, I've been doing this stuff for like 15 years or something like that. And so I think about it all the time. No one should have to be an expert in this stuff to use it. It needs to be something that's somewhat intuitive, and bringing these sorts of insights to people in their everyday workflows if we're not able to do that, then we basically haven't succeeded in solving the codependency that I was talking about earlier. So one helpful tool is SLOs. I'm not going to do a whole thing about SLOs because I think they're kind of common knowledge. But I wanted to just briefly mention something about SLOs in the context of resources and transactions. So SLOs, they're a hot topic. I would argue that SLOs are goals, and they are they're goals about a set of transactions that are scoped to a set of resources. So again, resources and transactions are a really nice way of thinking about SLOs. So I think the term service level objective, people often think, oh, service means microservice. Not really. Service level just means like, the service level for your telephone is that when you, well, sorry, no one has these anymore. If you were old like me, you picked up a telephone, got a dial tone, and the service level is that happened 99.99% of the time or whatever. It doesn't have to be a microservice, right? So the service level is just talking about how reliable are the transactions. Whether it means that they don't error out very often or that they're fast or what have you. And you want to examine that service level in the context of some set of resources. This is actually where the microservices come in, but you could also have an SLO for some other thing. Again, Kafka queues, databases, that sort of stuff. And in this way, the SLOs can represent a contract between these two dualities, right? Transactions and resources on one side and operators and end users on the other. So I think it's an elegant way to think about why SLOs are so vital and so important in bridging these two different worlds. All right, I wanted to, I know what I've said so far is quite theoretical, and I kind of hemmed and hawed about whether to just leave it at that or not. I decided I would show like a worked example of a real incident in a production system in these terms. It does show some like kind of product screenshot stuff, but this is not meant to be a demo or something like that. It's just meant to help illustrate, conceptually how this plays out in practice, specifically around a Kafka outage. And I've removed all the branding and stuff from these slides, so I hope that's okay. So here's a picture of a dashboard or a chart in a dashboard showing consumer lag for a Kafka queue, actually in Lightstep's own internal system. So this is a real, it wasn't like an outage that required an incident and stuff like that, but or it wasn't an outage that had a customer visible effect, but it was definitely something where people were scrambling to figure out what's going on. So you can see at 10:45 things were fine, and then they became not fine. So classic situation, you have Kafka, which is a distributed system in and of itself. It's a resource. Clearly something has gone wrong because it's getting really slow to do anything as a consumer. You're having to wait a really long time to get any data out of the Kafka queue. All right, so what do you want to do? Now, I think one option would be to try and like group by and filter this in various ways. What we really want to be able to do is just say, what changed in this resource? This resource has transactions going through it, a lot of them actually right here, and it also had transactions going through it right here. So what changed about the transactions between this period and this period? That's what I actually want to know as an operator, because that's probably going to give me a clue, because the code didn't change in Kafka, the workload changed. How? All right, so you should be able to click on this thing, and here you can see the query. You should be able to click on this change and say, okay, what caused this change? And then get to a UI where we say, okay, so here's the anomaly where the queue is unhappy. Here is a baseline where it was working normally. And again, we're just sort of zooming in to see what these two periods look like. And then what we really want to do is to understand statistically what's different about the transactions here from the transactions there. If we were in a normal talk and not a pre-recorded talk, I'd say, do people understand what I'm saying? I hope this is clear enough. We're trying to understand not just that Kafka is unhappy, but what's different about the workload here versus here. But the beauty is that there are tags. The Kafka queue has a name, the hosts involved have names, and the traces that go through the Kafka queue also are annotated with those tags. So we can actually join from this resource over to the workload and actually answer that question. Going back to those giant SQL tables I was talking about, we can say, okay, so let's just look at the traces that went through this specific Kafka queue, because that's a column in that giant table. Let's just look at the traces that went through that specific queue in these two different time windows and understand what other things are correlated with this regression. And what we see is that in this multi-tenant system with many different customers, there's a single customer whose project ID is 1753 that went from being 0.8% of all the traces to almost 16% of all the traces. So that's about a 20x-ish increase between this baseline and the regression. So that's actually really interesting. So some customer like significantly changed their workload. And that's exactly the sort of thing I'm looking for. The trouble is that customer tag is like way, way, way up the stack. It's not even available in the Kafka queue. Only by pivoting from the resources to distributed transaction traces are we able to understand automatically that there's a specific customer ID that's involved in this regression. And then, yeah, so here's this, now we get more detail on this by expanding it to say, okay, so we're, again, increasing by about 20x. And then, if you want to, we can view sample traces to see specifically what that customer is doing. And I'm not going to go into that. It's not the point. But what I'm trying to illustrate is that it's possible to go from this feeling to this feeling without writing any queries. Like you shouldn't need to be an expert to pivot from resources to transactions, but right now it's very, very difficult to do this actually, in general anyway. So I think that my vision for observability is that we stop talking about metrics, logs, and tracing as the point of observability. That's just the raw data. And instead we allow operators to understand the health of their application in terms of SLOs, understand the health of their resources, just as they do today, and then to pivot between those two things naturally without having to write queries, and to understand how the workload affects the transaction workload affects the resources, and how resource health affects the transaction workload without having to lift a finger or do any real work. So summing up, transactions, they traverse systems, use resources. Users don't give an SHIT about your resources, and similarly, DevOps can't do anything about individual transactions. They can only do things about their resources, at least not manually. And we must be able to use systems and use providers that join resources and transactions naturally to address the most important question in observability, which is what caused that change, whether it's a change in my transactions or a change in my resources. And that's really where I think observability is headed, kind of on this, within this framework of resources and transactions. All right, I think I'm done. I'm going to stop this recording and take questions. Thanks a lot.
Hi there, Ben. Thank you so much. That was a great talk.
Thank you. I'm glad to be here.
Great to have you here. So yeah, you did get quite a lot of questions throughout your talk that I saw you went through and answered. So yeah, I just thought it would be interesting as well to ask a few extra questions. So you spoke about the costs of storing data. So that's always like a really tricky conversation, I think, for folks. But what are your general tips there for having those conversations so that you can, minimize the cost but maximize observability?
Yeah, I mean, it's definitely a problem right now. I guess, I don't know, I have so much to say about that topic, but the first things that come to mind are, well, first of all, are we talking about transactions or resources, which is to say, are we talking about things like traces and logs, or more like statistical time series data like metrics? Because I think the conversation is different for those two categories of telemetry. But what we found, at least in my time at Google and then with Lightstep as well, is that it's not like it's not just a binary thing. Do you keep data or do you not keep it? It's like, do you sample it to begin with? Do you get it off the host? Do you centralize it over the wide area network? How long do you store it? At what granularity do you store it? And how does it degrade over time in terms of the precision? And when you see organizations that get very sophisticated about this, they actually have different answers along that entire life cycle for the telemetry. So I think it's a really challenging question to answer, because it kind of depends on like what granularity you're talking about. But the main thing I would say is if an organization doesn't have the capacity to profile their telemetry costs for that entire life cycle, including network, which is actually one of the largest components of the lifetime cost, is just sending the data. If you can't profile it, it's like any kind of optimization problem. You have to start there. And I think, frankly, a lot of organizations aren't able to profile it. Like you can't say which part of your application is causing you the most long-term telemetry costs. And until you can do that, there's no way to optimize it. So I'd start there. And then for folks that have done that, I think the main thing is being able to control the cost of an individual developer, like adding a line of code that adds too much cardinality to a metric. Like that can cost hundreds of thousands of dollars a year if you are doing it wrong. So being able to correct for that in a central place, I think, is the next thing to focus on. make sure that an individual instrumentation line can't balloon into some kind of unbounded cost for the platform team.
Awesome. Thank you so much for sharing. So another interesting thing too, I really liked your example at the end where you went through an incident that had happened and you shared on the screen. So Ben brought up Lightstep so you could actually see how it works. And I've used it myself as well. And I thought it was really amazing how quickly you could go down to an actual specific customer doing a certain action and it causing an incident. And I know for myself, like this has happened so many times over my career working on production systems. And being able to get down to that really, really small, like granular level super fast is very effective. So I saw we had a question in the chat. What was the web interface that was able to output the important differences given 2 time intervals? Did you want to talk a little bit about that, Ben? Like, your thoughts around that, like how different interfaces can actually help people do a better job. Like it's a big thing.
Yeah, sure. I mean, this is an editorial talk, and as I said during the recording, I hesitated to show that. I just literally I don't know of any other way to show it, and I feel like it's too abstract if I don't show something. So yeah, I mean, that to answer the literal question, that was Lightstep's product, but there's no reason why it couldn't be done, somewhere else if you can do the integration at the data layer. I think the thing that makes it difficult in practice is that the integration between the resource metrics data and the transaction tracing data has to be done at the data layer. You can't just do it via hyperlinks because there's what I described as a join is actually a join. Like you have to be able to join from tags in the metrics over to tags on groups of thousands of traces. And to do that requires some data engineering at the platform level. And I'd love it actually to see more solutions in the open source world go in that direction. I do think that that's it's the shortest path for incident resolution for sure, is being able to pivot via tags between time series data and transaction data. But it's actually a difficult problem if you have to start with like a siloed metrics solution and a siloed tracing solution to do that from like the web UI, because the integration has to be at the data layer, and that's what makes it so tricky from a product standpoint.
Yes, definitely. Yeah. And I've seen some platforms be created internally at places I've worked, but it takes, many years and a lot of iteration to be able to get it to work right. So not at all easy. The interesting thing too, like when you do have access to systems like this, say, for example, you have one customer that suddenly changed their pattern, but maybe it's great, right? Maybe they've onboarded all these new users and like a whole bunch of amazing work is happening. It means you can then actually say to other teams, like maybe the business side of the company, hey, like looks like this customer is doing really great work. Like you should probably know about that. Did you know they were even doing that? So it enables engineering teams to have like better conversations with really interesting and insightful data, which I think is good too. So we had another question here. What are your recommended tools to, what's the recommended tools to get tracing? It's always a service mesh or something similar, or is it better to do it individually inside of the system?
Yeah, I actually did a talk in, I think it was 2017 at KubeCon about service mesh and tracing. And there's I've bad news for the person asking the question. I guess it's Fernando, right? Service mesh is helpful, but absolutely does not solve the problem. All that service mesh really does is give you telemetry about, the calls between services. But the hard part of tracing, well, at least the hardest part of tracing, has always been successfully propagating this like trace ID context from ingress in a service through, the function calls out to the egress from that service. And the service mesh has nothing to do with that. The service mesh only handles the calls between services. It's within the service is the hardest part of tracing, and it doesn't really help. So you end up with a bunch of data about, point-to-point data with the service mesh, but to actually successfully address the context propagation problem, the only advice I have would be to move towards open telemetry, which actually is trying to address that problem in a pretty comprehensive way and make that sort of context propagation a built-in feature. And indeed, open telemetry will also integrate with service mesh, but there is part of the pitch for service mesh is that it solves the tracing problem, and it's just not true. It adds data for tracing, but it doesn't solve the context propagation problem. That's actually at the core of distributed tracing. I hope that's helpful.
Yeah, thank you. And there's another just question around open telemetry. So what's your thoughts there?
I mean, I'm extremely biased in that I'm on the governing committee and I co-created the project, but it's, you know, it does seem objectively to be a very successful project from the standpoint of, you know, having many contributors. I think we have 1,000 contributors in the last month alone, and, you know,
Wow.
every major vendor and cloud provider has bought in and is staffing the project and so on. So the only issue with OpenTelemetry is that it has so much activity that we're having some difficulty just literally maintaining the project. But it's, I think the reason it's been so successful is that it benefits many parties. It's just kind of a win-win for, you know, major infrastructure providers, cloud providers, observability vendors, and especially for end users, because you can end up getting high quality telemetry without binding yourself to any particular vendor or provider. And that kind of portability is a very attractive thing. And I think, you know, observability solutions have long been constrained by the quality of the telemetry they can collect, and OpenTelemetry like really is going to rise that tide, and then you'll see solutions improve as a result. So, I mean, OpenTelemetry, yeah, it's a very exciting project. I think the only thing we really need is just to be able to say no a little bit within the project, so that we can hit our milestones. It's been a victim of its own success to a certain extent, but it definitely has a bright future, I would say.
That's great. Do you have a few things to share for the roadmap of OpenTelemetry just over this year? A few things you're excited about?
Yeah, I mean, the most exciting thing to me is that the OpenTelemetry, so I was saying the three pillars of traces, metrics, and logs don't really make any sense for observability, and I will hold my line on that, but they definitely make sense for telemetry. So those three aspects, we started with tracing. That's basically been GA at this point. Metrics is coming up soon. And then logging will come later. I think it's actually the least important of the three for OpenTelemetry to address from a standards and API integration standpoint. So I'm very excited for metrics to get past that point. And we're also doing a lot of work with the Prometheus community to make sure that there's interoperation between Prometheus and OpenTelemetry, so that you won't be forced to choose. And I think that's also going to be a really good thing to see that stabilize this summer.
That's awesome. Yeah, I'm sure we've got a lot of Prometheus users watching along right now as well. And I guess we've only got time for probably one last question. So there is another question here, a common question around the performance cost associated with distributed tracing. So what's your thoughts there?
Yeah, and by the way, I think, you know, I'll go to the Hangout the speaker thing after this.
Yep.
So I'm happy to continue this conversation. But yeah, good question. I mean, distributed tracing does not need to have any overhead from a latency standpoint. There is some kind of minimal marginal throughput overhead in the sense that it does take resources, but usually people can adopt some kind of sampling to address that. The Dapper paper that I helped to write at Google describes and details our measurements for performance, but it was imperceptible in the sense that it was in the statistical noise. And Dapper runs 100% of the time for 100% of Google services and has for like 15 years. So it's definitely not like a high overhead thing if it's done correctly. And that's one of the beauties of it.
Awesome. Well, thank you so much, Ben. So we've reached the time allotted for this session. We invite everyone to come and join us in the Hangout with the speaker in the Zoom room. So you can find that on the schedule, and it'll be just an informal opportunity to ask questions and share your thoughts with Ben. So please turn your camera on when you join there to chat and ask questions. Thank you so much, Ben, and thank you everyone for attending.
Thank you so much.